Alright, hi everyone, this is Mr. Zarzak, and in this screencast I'm going to take you through the law of reflection. So what we're looking at here is I have a white surface and I've got a little mount for a little mirror. This would be the kind of mirror that you would use in the plane mirror lab, so you can see my reflection there. Hello! Okay, so I've just got this mounted on this little stand. Alright, and if I turn on my laser over here, so I got a laser on the side of the screen, you can kind of see it poke around. Okay, it strikes the mirror. When it does so, you can see that it makes an angle with the mirror. So if I go ahead and I just mark that, okay, that angle there, that's what we would call the angle of incidence. So I label that angle I to stand for incidence. All right, and if I take and I label this angle over here, okay, that's what we call the angle of reflection. Okay, and just kind of looking here, I hope you can see this alright on the video, but the size of these two angles is exactly the same. If I pulled out a protractor and I measured it, I'd see that those two angles were exactly the same. If I instead took and I changed my angle of incidence here, so I'm just going to shift this over a little bit. So something like that. Okay, well now both my angle of incidence and reflection have changed. So here, let's just go to the extreme here. I'm trying to make my angle of incidence really close to the side. You can see that the angle of reflection is getting bigger too. Okay, no matter how big or how small I make my angles, okay, the fact that those two things are the same always remains the same. So if I write that down as the law of reflection, so the angle I equals angle R. Now, for a plane mirror like this, it's really easy to measure relative to the mirror, but you'll see that as we go farther in optics, we actually have another trick that we use to measure these two angles. Okay, and so to help you see this, I have a second laser here. Okay, and the reason I've got it in green, I've got it shooting straight at the mirror, so when the light bounces off, it just bounces straight back. The reason I've got this set up like this is so that you can see this other way that we measure the angles. All right. This green line that comes perpendicular at 90 degrees off the mirror, we call that the normal line. Okay, so that's the normal line. Okay, and so when we make our measurements of the angle of incidence and the angle of reflection, we always make it relative to this perpendicular line that we call the normal line. And so if I just go and I mark my angles here, this is my angle of incidence. And then this over here, that's my angle of reflection. And as I change my angle of incidence, you'll see that my angle of reflection changes too. So see here, I made my angle of incidence larger now. But in doing so, I also made that angle of reflection larger. See, and so this is going to hold true for any angle. So no matter how big I make this angle of incidence, the angle of reflection gets really, really big. If I make this really, really small, the angle of incidence gets smaller, but so does the angle of reflection. So here, I can just erase that real quick to show you. Okay, and they always obey this rule, this angle I equals angle R. That's the first part. Okay, so for this next part, I've reset the board. I've got the mirror back here in the middle. I've actually gone and taken a marker and I've drawn a line across my board here just so that if I need to put my mirror back in place, I've got a location to show me where to put it. Okay, and then the other thing I've added here is this is a little magnetic push pin. Okay, that you get. So it's a push pin without instead of the little pin to push into like a cork board, it's got a little magnet. And I marked the location where I want it with a little dry erase marker spot just so I can put it back if I need it. All right, and I've got my lasers over here, so I'm just going to turn on one here for a second. And you can see that I've got it set up so that the light goes and bounces off the mirror over to the little push pin. That light is following the law of reflection that just says the angle of incidence is equal to the angle of reflection. Okay, so well, here's the hitch. All right, if the angle of incidence is equal to the angle of reflection, well then I can reverse that. Okay, so think that there's going to be some light traveling from this pin to the mirror. That light would hit the mirror and would bounce over in this direction, okay? And so what I want you to do is imagine that the laser, instead of being the source of the light, is actually you looking into the mirror. So it's like your eyeball, Okay, and what this is telling me is that if I want to see the pin by looking at the mirror, this is exactly where I would need to look at the surface of the mirror to see the pin. Okay, so we're just taking that law of reflection and flipping it around on itself. Okay, so if I think about it this way, this line here becomes what we call a line of sight. If I put my eye here, this is the line, this is where exactly where I need to look to see the reflection of the pin in the mirror. Okay, now I have a second laser, okay, lined up over here, and you can see that the green line is going to the mirror and it's bouncing off and it's going right to the pin. Because the green laser is at a different location, the location that we've got to put it to hit the mirror is a little bit different for this red. Okay, now this is still following the law of reflection. The angle of incidence is equal to the angle of reflection. All right, but the point is that if we think of this green laser now as your eyeball and you're looking in the mirror at the pin, where you would need to focus your sight, or where your line of sight would go, would now to be a different part of the surface of the mirror to see the pin. If I do this one more time, okay, so now I got another laser over here, and you can see that the light's bouncing, hitting the mirror and going straight to the pin. Okay, and so what we have to do is imagine, now I've taken and I've moved myself over here, so this is my eye, and I'm looking into the mirror to see the reflection of the pin. Well, where I have to focus my vision is along this line of sight, to where I'd be looking right at the surface of the mirror right here, and that's where I would see the pin. Okay, so now here's the kind of tricky part, the next phase to this. All right, we've already shown that the angle of incidence is equal to the angle of reflection. Okay, we've got that part. All right, but the real point of this now is if I take away the mirror, okay, and I leave the lasers on, you can see that they all come together over here. All right, at that one point, the lines come together. We have a word for that. It's called converge. Okay, and the deal is this convergence point is really where we see the image of the object when we look into a plane mirror. And this is kind of weird. Okay, I'll show you what I mean by this in a little bit, but just stay with me for the time being. All right, this point here, this is the image location, whereas this is the pin back here, this is the object location. When we look into a plane mirror, believe it or not, the images that we see are somewhere behind the mirror. And what's even better than this, okay, is the law of reflection says that the angle of incidence is equal to the angle of reflection. But when we see an image in a plane mirror, something else holds true. If I move this out of the way here, okay, and I bring in a meter stick, okay, if I go and I measure how far it is from the pin here to the mirror, okay, hopefully you can see this, okay, it's 16 centimeters. Okay, and in fact, let me turn some light on so you can see this, okay. That location is 16 centimeters. Now, if I go and I put my meter stick over here on that little dot I drew where the laser light came together, this distance here is also 16 centimeters. Okay, and so when we make our measurements with a plane mirror, we say that if the distance from the mirror to where the thing is the object, so we call that object distance, we call that DO. If this was 16 centimeters, well, then the image from the mirror to where that light comes together, that convergence point where we see the image, that's DI, that's my image distance, that's also 16 centimeters. So for plane mirrors, we have two rules. We have the angle of incidence equals the angle of reflection, and we also have that the object distance is equal to the image distance. And so summing this up, what this really says is that when we look in a plane mirror, the image that we see is located the same distance behind the mirror as the object is placed in front of the mirror, and that object is also located at the same angle. Okay, hi everyone. So now I'm standing in front of a mirror down in my basement. All the previous videos were shot down here as well. I think it's kind of ironic that physics is going underground, and well, here we are in my basement underground. But anyways, I'm sure you're curious about this, so just a quick look around. We've got this set up for the kids. So we've got like beanbag, and over here we've got playground, and there's a trampoline, put in a bowling lane, and rocket ship. So, you know, the typical stuff that you have. Okay, so anyway, so the reason I'm standing in front of this plane mirror, okay, is to try to show you what I mean when I say that the images that you've seen are formed somewhere behind the mirror. So I'm standing in front of the mirror and I'm looking at an image of myself. From my perception, it's almost like I'm looking through a window, looking at an image of myself talking, well, right back to me, doing whatever it is that I'm doing. The early name for a mirror way back in the day was called a looking glass. Okay, because mirrors are made out of glass, and you look into them and you'd see things almost like you're looking through a window. Anyways, so if I look straight ahead, I see myself staring back at me in the mirror. But if I start to change the angle, okay, that I'm standing in front of me, so I'm just walking to the left here. Okay, so the things that I see being reflected off the mirror, okay, are coming from the side. So like if I keep going like this, our rocket ship kind of comes into view. You can see it over here, and if I go the other direction, and I can keep going. It's not that exciting. There's the bowling pins. Okay, so it's almost like I could just as well think about this as like I'm looking through a window at an exact replica of my basement. So that's the first part. Okay, when we talk about the images we see appear to come from behind the mirror. All right, but there's something more to it that I think will kind of help drive this point home. And so I've also got this metal board here, and on this metal board I'm going to put an eye chart. Okay, so this eye chart is not a legal eye chart, it's just something we printed off. Okay, just kind of as a gag. All right, so what I'm going to do here is I'm going to walk back, and I'm just looking in the screen right now. What I'm trying to do is just kind of get an estimate of how far I can go back to where I can still read the bottom line. And to me, I think that F, X, O, X, R, X, A, X, L, X, L. So about here, okay, is about the limit of how far I can move and still read the eye chart. Okay, so I'm going to go back and I'll take the eye test here again in a second, but before I do, all right, something I want you to see. I have a second eye chart, okay, and I've got it stuck up on the wall here, and you can see it's the same size here. Maybe I should put it side by side. Okay, yeah, let's do that. So put it side by side this series. You can see that it's got all the same letters, okay, it's just the letters are printed backwards. Okay, so now why am I doing this? All right, well, let me walk back again. And all I'm trying to do is find where to stand, sorry for the little wiggly on the camera, okay, to where I can just barely read that bottom line, F, X, I can still read that there, so let's try going. That's about as far back as I think I can go. It's already kind of fuzzy. Okay, well here's that other eye chart. Okay, and now if I put it up and say, all right, well, let me try to read that bottom line. No way, forget about it. Okay, well, why is that? Well, if I'm standing, I know it's science class, but let's just say I'm about 10 feet, okay, from the mirror right now. Okay, well, the image that I see is formed somewhere behind the mirror. How far? Well, if I'm 10 feet from the mirror, well, that means that the image I'm seeing is also 10 feet behind the mirror, which means that the total distance from me to the image that I see of both myself and of this little eye chart is 10 plus 10 is 20 feet back. And if I hold the eye chart up next to the one that's stuck to the wall, I mean, you can see it. Everything is half the size. Well, why is that? Well, because from our perception, everything is now twice as far away. With a plane mirror, the images that we see are formed just as far behind the mirror as the object is placed in front of the mirror. This is the object that I've got clipped to my iPad. The image I see is somewhere behind the mirror. Double the distance as the object distance. Okay? So I hope that helps you understand this thing that we call the law of reflection and how we get images in plane mirrors. Just as a quick little wrap up here, when we see images that are formed behind the mirror, we call those virtual images. So virtual is just another way of saying imaginary. Okay, so more to come. Thanks for watching. See you next time.